As mentioned in the beginning of this chapter, it is possible to assign 4 unique quantum numbers to each electron inside of an atom. And if you're going to do that, the m sub s values start becoming more important. And you need to realize that m sub s values are actually affected by other rules. So one of the rules is called the Pauli Exclusion Principle, and it says when 2 electrons occupy the same orbital or m sub l space, their spins must be paired. So if I put the first electron in and I call it spin plus 1/2, then the next electron must be minus 1/2. And here we're going to represent the spins by using arrows, an up arrow being spin plus 1/2 and a down arrow being minus 1/2. The next rule is called Hund's rule, and this one tells me when I have more than one orbital in a subshell, so say I have 3 m sub l's or 3 orbitals, that 1 electron must go into each one of these orbitals before I start putting 2 electrons into the same orbital. So I must put 1 electron into all of my m sub l's before I start pairing them into the same m sub l. Also, Hund's rule says that when I do this, these single electrons need to have the same spin, or what's called spin parallel. So all of these electrons need to have the same spin before I can start spin pairing them in the same m sub l. So let's look at an example. Here I'm given a 3s subshell, and what I'm going to do is put 2 electrons in there and assign each of them a proper quantum number. In doing these kinds of problems, the first thing I want to understand is how many m sub l's do I have? How many orbitals do I have to put electrons into? When I'm dealing with a 3s subshell, I know that the L value is equal to 0, and I know this because we're dealing with an S subshell. When L is equal to 0, my only possible m sub l is equal to 0. So that means in an S subshell, I can only have 1 orbital. So I have 1 box that can hold 2 electrons. Then what I do is I draw a box representing that m sub l, and then I make a column for each one of my electrons. So here we're dealing with 2 electrons, and then I make a row for each one of my quantum numbers. And you're going to find that this helps keep track of all these quantum numbers. The first 2 quantum numbers, N and L, are the easiest to find because those are given to us when the orbital subshell is given or designated. So here we're told we're dealing with a 3s subshell. So this tells us our n value is equal to 3. So that's what the 3 means here, is n value for all of our electrons. Also, by saying that the subshell is S, it told us what the L value is. So when S is my subshell, L values must be equal to 0. Lastly, I only have 1 m sub l, so for an S subshell, I only have 1 possible m sub l value. M sub l is equal to 0. So that's going to be the m sub l value for both of my electrons. And then what I do is I start adding electrons. So here I have a decision. I can put the first electron being either plus 1/2 or minus 1/2. Doesn't matter. I've decided to make my first electron plus 1/2, so I have an arrow going up. When I go in and put the next electron, the Pauli Exclusion Principle says that these 2 electron spins need to be paired. Because the first one was plus 1/2, the second one needs to be minus 1/2. So here I've assigned a set of 4 unique quantum numbers to each of the 2 electrons in my 3s subshell. Looking at another example, I'm putting 5 electrons into a 2p subshell. I also want to give them a set of 4 unique quantum numbers. Still, the first thing I want to do is realize how many m sub l's or orbitals do I have. So the L value for a 2p subshell is 1, and I know that because we're dealing with a p subshell. When L is equal to 1, my possible m sub l values are minus 1, 0, and plus 1. So that tells me that we have 3 orbitals to put electrons into. So I like to draw a diagram, have 3 boxes, 1 for each m sub l value. Then I make a table here, a column for each electron, and a row for each of my quantum numbers. Remember, the first 2 quantum numbers, N and L, are very easy. They're given to us in the orbital designation here. we're playing around with a 2p subshell, so we know that the n value for all of my electrons are going to be 2, and that's given right here. Also, I know what the L value is for all of my electrons because we're dealing with a p subshell. So when we're dealing with a p subshell, L value is equal to 1. Then I start putting in electrons. First electron goes in the m sub L that's all the way to the left, and I decide I'm going to make my first m sub s plus 1/2. So down here you can see where I'm filling it in. I put the first electron in as plus 1/2, and then Hund's rule takes over. So when I put in electron 2, so here in electron 1, I put my first electron into m sub L minus 1, and then I said it's going to be plus 1/2. Hund's rule says that the next electron to go in is m sub L is equal to 0. Hund's rule also tells me that the spins need to be parallel. So if the electron in my m sub L minus 1 is plus 1/2, then the electron in my m sub L is equal to 0 must also be plus 1/2. Same deal when I go on and I put my third electron in. Hund's rule says it needs to go into m sub L plus 1/2. I need to put an electron into each one of my m sub L's before I start pairing them. Hund's rule says that this electron also needs to have a spin of plus 1/2. So now I have one electron in all of my m sub L's, so when I go to my fourth electron, I can go back and start putting a second electron into my m sub L's. So the next electron goes back into m sub L minus 1 here, and the Pauli Exclusion Principle says that the electrons need to be spin paired. So the first electron that I put in there I said was plus 1/2, so now the next electron needs to be minus 1/2. And then as I continue on, the next electron goes into m sub L is equal to 0, and this also needs to have a minus 1/2 spin because the first electron here has a plus 1/2 spin. So now I have assigned each of my 5 electrons a unique quantum number.